Okay, welcome back. So we're looking at today distance, time graphs, velocity, time, speed time, displacement time. Look at all those different values, and we're just basically going to put all those together in terms of the graphical relationships. The next video will hopefully start looking at derivations using these graphs, edging towards Suvat equations. Now those derivations, we'll talk more about them when we get to them. But first of all, we're looking at distance and speed. So speed is the rate of change of distance. So we're looking at that and the difference between distance and displacement. We'll come across that in a second. First of all, I just want to show you a small demonstration in terms of like a racetrack, for example. So looking at a racetrack, so this is an oval racetrack, and if you've got a person racing around that track, then if we have a total circumference of that track, or total path of that track, which is equal to about, I don't know, 30, well, we'll say 100, no, we'll make, let's say about 400 meters around a normal track, 400 meters. That means after he's run around once, he has travelled a distance of 400 meters. The difference between that distance and displacement is that at this point, when he's run all the way around the track, his displacement is 0 again. Okay, I'll say that again. His distance after running all the way around the track, he's travelled 400 meters. However, his displacement is 0 meters because he actually hasn't displaced himself from where he started as a result of that travel that he's undertaken. So that's a nice way of realising that displacement is a vector quantity and distance is a scalar quantity. So this quite nicely highlights the difference between the two. Right, let's look at distance time graphs first of all before we go any further. So distance time graphs look something like this. So we've got distance and time. Now, that's a standard distance time graph. Now, there's a lot you can tell about a straight line. So when it's directly proportional, we can tell something's happening. Now, from GCSE, what you might remember is that speed is equal to distance over time. That's one that you will have learned from your GCSE physics lessons. And you might then realise that there are certain properties of this graph that allow you to come to an understanding of different values. So for example, if we're looking at this, the feature of this graph that is the gradient. Now, we won't talk too much about gradients now, but we will do a video on some mathematical techniques at a later date. So the gradient of this graph, change in y over the change in x. So that y divided by x in this case is the distance, that is the time. So if you divide those by each other, the gradient is equal to the speed. So the gradient on that line is equal to the speed. Triangles, when you're drawing triangles on a straight line, please make sure that you've got, that you don't use a nice big triangle. Don't just take a triangle at the top there, that's bad. The reason that's bad is because you're basically saying, I don't need all that data. What was the point in you collecting it if you weren't going to use it? So use as much data as possible to collect it, or to get your speed from your gradient. Okay, next step. What happens when it is not a straight line? Say it's a curve, or what's happening there. So if we look at this curve here, so I've drawn a nice gentle curve there. First of all, we want to explain what is happening between what we first drew and what we drew now. In the first instance, it was a straight line, so anywhere on that line, the speed would be the same. So that's meaning that there's the vehicle, the car, or the object that you're describing the motion with this graph was travelling at a constant speed. However, it's changed. How has it changed? This one has changed because the gradient is getting steeper and steeper and steeper and steeper. So, what does that mean about the speed? Steeper gradient means a greater value of speed. So, in this case, how would we work out the speed? Well, we couldn't work out the speed across the whole lot. You'd end up working out an average. We don't want an average in this case, we want an instantaneous. So how would we work out an instantaneous speed? Well, what we would do is we'd take a tangent. So at a point on the line that we want to work out the speed of, you look at that and you go, okay, right, so I've got, and we draw a line at a tangent to the curve. Now a line at a tangent to any curve, so if we draw a curve, so if we draw a point there, it's a straight line that intersects, and where it intersects should be a nice point. Now I've not done a great job of that, but hopefully you understand the idea there. Once you've got your tangent, you can then do a triangle based on that tangent to give you an approximate speed. Again, delta y, delta x, based on those scale axes. And so we can then work out the instantaneous speed there. So delta y divided by delta x. And that will give you an instantaneous speed for that point in time. Remember, if you did the whole lot, it would be an average speed. Right, let's look at some of the features of these. So, nice thing to say about this one. We've said it's an increasing speed. So what does that, how else could we describe an increasing speed? Well, we would say that it was accelerating. Interestingly enough, we can only tell so much about this acceleration. We don't know whether it's a constant acceleration or not, so you try not want to jump the gun. You don't really want to jump the gun with that, but you can say that it's accelerating because we're increasing the speed because the gradient is increasing on this graph. Right, so let's try it with a different one, just to make sure you're happy. Okay, you might want to pause the video. What does this mean? Right, so if you've paused the video, you should have an idea of what this means. You do want to write that in your notes, see if you could guess it right. This essentially means we've got a very high speed going to a stop. Okay, now notice that if we've got a flat line on a distance time graph, that means there's no gradient. Gradient of zero, and so we've got zero speed. So what we've got here is essentially a deceleration to zero speed. So we're not moving at all when we get to that point. We're not changing the distance at any time. So this is a deceleration, whereas the previous one like that would have been acceleration. We can use exactly the same method as before to work out an instantaneous speed. Tangent, gradient line off that to give us an instantaneous speed at any point in time that we're interested in. Okay, so we've already talked about the difference between distance and displacement, but let's actually look at displacement time graphs. And let's have a look at the kinds of things, the kind of expectations that we would see. So, we're now going to go for a displacement time graph. Now this is going to hurt you a little bit because you'll notice that I've written S up there because S is used for displacement at this level. Okay, so don't be too thrown out by that. I know we were using S for speed before, but we were dealing with speed equals distance over time. Sorry, just got to suck it up. Okay, S in this case is displacement. So for a displacement time graph, we can make all kinds of other conclusions about what's actually happening. So a displacement time graph that looks like this is not too dissimilar from the distance time graph that we just looked at. The distance time graph was exactly the same first one, and essentially this is saying exactly the same thing. We're changing the distance at a constant rate, and so therefore we've got a constant speed as we travel away from our origin point, worked out by the gradient as I've shown there. The only difference now that we see is that things can actually change direction on a displacement time graph. Whereas distance travel was irrespective of direction, you could keep going and going and going, and you'd always increase your distance, you could never go backwards. With displacement, you can. As I showed you at the very beginning, you can go backwards. So let's have a look. So if we drew something like this, then we're being told a story now about what's actually happening. We started off travelling away from our initial position at constant speed until we came to a stop. Now, yes, this is a displacement time graph, but a flat line, exactly the same as distance, would mean zero speed. It's not moving. So we've stopped for a certain amount of time. So that's stopped. Pause the video for a second and decide what you think is about to happen next. So you should have paused the video and had a look. See if you got it right. What's happening here is it's going back towards its original position. When you've got a negative, when you've got a negative gradient there, that means it's still moving. It's got to be moving. It's got a gradient, but it's traveling in the opposite direction. It's coming back to where it came from in the previous instance. So in this case, it's coming back to itself. Now, you might have also drawn another conclusion, which is the conclusion that this coming back is faster than what it was moving away. You can make that conclusion quite simply because this line is less steep than this one. This is significantly steeper than this. So this would be kind of an average speed. It's not too slow. And then this one would be much quicker because its gradient is much steeper. Again, you can work out the gradient in the same way, delta y over delta x. Delta just means the change, okay, if you weren't aware of that. So that's a very simple kind of view of displacement time, of a displacement time graph, okay? So let's look at velocity now. Let's look at velocity. First of all, what is velocity? Well, velocity, represented by the letter V, is displacement over time. Again, I know it's a bit of a mind meld. You've got an S and a V, which is which, but it's something you just get used to over time. So, it's the change in displacement over an amount of time. Now, how can we write this in words? If we were asked to define this in an exam, what would we say? Well, the best way of putting an equation like this in words is saying the rate of change of displacement. Now, that can be used for lots of other things. You're going to see that in acceleration and even in momentum when we study that later on. When something is being changed in an amount of time, then essentially what you can say is the value of velocity is the rate of change of displacement. Rate of change of displacement. You must say the rate of change of displacement, not distance, because distance is obviously a scalar quantity. Velocity is a vector quantity and so relies upon displacement, which is also a vector quantity. Okay, so you need to be very, very careful. Choose your words wisely. So, we can draw a velocity time graph. So, velocity time. Let's draw a nice simplistic view here. There's a straight line. Nice straight line. Now, careful, straight line on a distance time or a displacement time was stopped. Is this stopped? The answer is no. It's not stopped. It's got a constant velocity. It's got quite a high constant velocity as it travels through time. The only way something can stop on a velocity time graph is if it hits 0. That's when it's stopped. That's the only way it can stop. Now, here's a problem though. We can extend our velocity time graph into negative values. Well, what does this mean? Okay, well, it's all to do with the fact that velocity is a vector. It has magnitude and direction. magnitude and direction. So here, what we're saying is we were travelling in one direction with a positive velocity, and then we travelled back with a negative velocity. Show you again. So this, I'm demonstrating what you're seeing on this graph. Okay, you saw me stop instantaneously, but my velocity changed instantaneously to become a negative because I was coming back. So that's what I was demonstrating there. Okay, so you need to be wary of this. At a point where it hits here, a straight line down the middle there would be a stop, 0, and it's an instantaneous change. I've changed direction, therefore it's become a negative value. Notice that the magnitude, my drawing is not great, is about the same, so we would expect my magnitude of velocity, the rate of change of displacement, to be about the same. Okay? So here is a nice velocity time graph, and velocity time graphs are lovely questions to talk about bouncing balls, things being dropped, things being thrown in the air, and we'll do some examples of those when you come into lessons. What you might want to have a look at before you come to the lesson is some examples of a bouncing ball or a ball being thrown up in the air, velocity time and displacement time graphs. If you're really, really great, then you're going to have a look at things traveling in a circle and look at velocity time graphs and displacement time graphs for things moving in circles. Okay, that's kind of what we're going to do to step up and advance ourselves in this area. For now, we'll leave it there. Next time, we're going to delve a little deeper into some of the graphs that we've seen, and we're going to do some derivation around those to work out some SUV-apt questions. So what you should do is have a look at some of these graphs. They're not as simple as they seem. They do get more complicated, especially when they go into negative values like we've seen on the board there. And you might want to have a look at, when we haven't got straight lines, things like this on velocity time graphs. That is something that you'll want to have a look at, make some notes on, and we'll discuss that when you come to class. Okay?